In this video, we're going to take a look at electrophilic substitution reactions as well as its mechanism. So to start off with, benzene undergoes electrophilic substitution reactions. Now, benzene itself doesn't undergo addition reactions, but benzene is attracted to electrophiles because it has a ring that has high electron density. We've got that delocalized cloud of pi electrons here that will attract electron deficient species. And what results is that we actually get a substitution for one of the hydrogens with the electrophile. So in general, you will create the product with the electrophile attached, and then you will create an H plus or lose a hydrogen atom in this particular reaction. So these reactions are known as electrophilic substitution and not addition because we're substituting a hydrogen with an electrophile. So let's look at some specific examples of electrophilic substitution. Now, I think the hardest part here is knowing what the electrophile is going to be in each of these different scenarios. So starting off with the first one, benzene, if we react it with nitric acid and a catalyst of sulfuric acid, the reaction and the mechanism that happens in this first step, which we don't need to know, but essentially it's going to generate an electrophile that's NO2+. And so it's known as the nitration of benzene reaction. What we're going to create then as our products is a benzene with a nitro group attached to it. And then we're creating a molecule of water as our other product. So we're going to lose an H, the other HO from the nitric acid bonds to that and creates a molecule of water. For our second reaction, essentially we generate a Cl plus as the electrophile here. And so what we're creating as our product is a chlorobenzene. And then our other product is going to take the other chlorine and an H and create HCl as our product. This generally requires a catalyst of aluminum chloride. So we need to make sure we add that when we also talk about this reaction. Similarly, in the next reaction, we have a Br plus as our electrophile with an iron 3 bromide catalyst. And so that's going to create a bromobenzene and HBr as its products, as its other product. And then finally, we could add any kind of alkyl halide. And so essentially this creates an R plus electrophile. And what we end up creating, we need an aluminum halide. So the halide needs to be the same halide as in our thing that we're reacting with here. But essentially we're creating an R substituted group here, and then we're creating HX as our other product. So there's lots of variations of electrophilic substitution, but they all kind of follow the same method and the same type of reaction mechanism. So let's take a closer look at this reaction mechanism that happens here. Now, in general, what happens is we first get, similar to an electrophilic addition reaction, is we get our delocalized pi electrons, which are acting like a nucleophile, right? Because it's an electron-rich area attacking our electrophile. Very typically, this first step is very, very slow because we're disrupting or taking the electron pair, and we're disrupting this delocalized pi system. So what we create is a carbocation intermediate with an H and an E attached to one of the carbons in the ring. And so we show a delocalized pi system being interrupted by drawing in this half circle that's a dotted line with a positive charge, okay? And then this intermediate, this carbocation intermediate is really, really unstable. So what happens is typically the catalyst will come and pick off this hydrogen atom here. which breaks the bond between the H and the carbon of the ring, drops the electrons back in the ring to create just our substituted benzene ring with the electrophile, and then an H plus as our other product. Okay, so very sort of generalized. This first step is super slow because we're disrupting that delocalized pi system. And then the second step is fast because this is super, super, super unstable. So let's look at a specific example of how this mechanism looks in the next sort of part of our video here. So going back to our reaction of the nitration of benzene, we don't really need to know this step here, but like this is kind of step one of our mechanism, is we're taking nitric acid and sulfuric acid, which is our catalyst, and we're generating our NO2 plus, which is our electrophile, and we're also generating this HSO4 minus, which is going to come into play in the rest of our mechanism. Okay, so in our first step of our mechanism here then, the electrons from the pi bonds are going to attack our NO2 plus electrophile. It's going to create our carbocation intermediate with both the NO2 and the hydrogen attached to this carbon with a positive charge and our half ring here. And then our catalyst, our HSO4 minus that we generated in that other step, is actually, and I don't like this arrow because this arrow is not drawn right, it's going to come and pick off this hydrogen here, which breaks the bond between the H and the carbon, regenerating our benzene ring and regenerating our catalyst. So this is why it's a catalyst, because we use it up in one step and then we regenerate it at the end of our reaction. So this is a great example of how this particular electrophilic substitution mechanism works. Those are our electrophilic substitution reactions then of benzene. That's it for this video. We'll see you in the next one.